Okay, so last class we discussed a lot of line broadening. Essentially, we focused primarily on the various microscopic processes that we had. We had already dealt with the Lorentz function and the natural line broadening. Yeah. Now we discussed also the Doppler broadening part, that is from the random thermal motions in a gas, like here in the room, even though the gas on average is in hydrostatic equilibrium, so to speak. The individual molecules, in this case, in our hydrogen universe, the hydrogen atom, move around. So they're subject on an individual level to Doppler shifts. And when summed up over a Maxwellian velocity distribution along the line of sight, which is important, we will see today another example where we will use it for Bremsstrahlung, free emission, not bound, when we don't use the line of sight velocity. And then we got the Doppler profile, and then when we combine them, we got the void function with its characteristic Doppler core and Lorentzian damping wings. We also discussed why it's difficult for natural line broadening to actually be important. And typically, once you get it to be important with a simple example calculation, right? You're typically almost at the continuum level, in the noise, very far from line center. But there are instances where collisional line broadening are important. We discussed that in a qualitative sense, that it often has the same Lorentzian shape, so you get the damping wings, okay? However, we did not go into details there, and that is because the details there really is a little bit beyond the level what we can do in this course. Huh? But we can understand it qualitatively, okay? The collisional broad damping wings of lines. All of those were intrinsic processes. Then at the end, we discussed the effect of macroscopic velocity fields, where, for example, I took one example. We can call this the effect of macroscopic velocity fields or macroscopic line broadening. Yeah. One was when we had an unresolved source. An unresolved source could be like a globular cluster at a far distance, or an elliptical galaxy where we cannot resolve the individual stars. But we can take one integrated galaxy spectra, say, right? And then, of course, if you have such an elliptical galaxy, then your integrated spectra then will reflect, assuming that the light is dominated by the stars, the line spectra in this case, it will be a reflection of these stars, then motions, okay? If they are ordered or not. And of course, if you can say that these now individual sources all emit a little, say, a Doppler spectra themselves, which reflects then the thermal motions here, but then perhaps the bulk motion of this galaxy and their motions of the stars themselves could be much greater than that. And then, if this is negligible, yeah, then of course, if you say take the integrated spectra here, and you say that the line, I don't know, looks something like this, if it's an emission line, then you can look at the shape of this line and get an estimate from the shape of this line on the velocity distributions of these stars. For example, if they follow a Maxwellian velocity distribution, okay, that is the stars themselves, then of course the total then integrated line spectra here will be that of a Gaussian, analogous to what we did for the intrinsic line profile. And then you can measure, say, the full width half maximum, or get an estimate of the velocity dispersion, as we have learned how to do, in order to get the measurement of the velocity dispersions in these galaxies. You can also do more detailed studies in looking at the different shapes of the lines to see if the orbits of the stars perhaps are more elliptical or more radial, yeah, schematically, because this will give rise to different shapes of the line profile functions then. If they deviate from a an isotropic Gaussian. Okay, so that's how you can use it in an integrated sense. Right. There is also this that we can see that this sort of adds these type of macroscopic velocity fields we can also have in the individual objects themselves, right? So in that sense, you have another Doppler shift, say, that your new prime, call it then, is your new, and again, this is subject to the velocity, where this is now the line of sight velocity, which I skipped the subscript, yeah? And we know that we can approximate this with roughly nu0 v divided by c, right? So then if we just make the simple thing that we take minus nu and we divide it by delta nu d, we know all about these quantities from last week now, so we're not going to then we can see that we can, of course, write this in this form again. So that we can write this as sort of x prime equals to x minus v divided by v thermal, okay? So if we now have a shift so that we have a Doppler profile around the atom's own frame, so that the atom, as it is moving here in this bulk velocity of the gas, now has an intrinsic profile that can be approximated by a Gaussian, then of course that Gaussian will be of x prime dx prime then e to the minus x prime squared divided by square root of pi, right? Dx prime. But if we write this in terms of our in the x space, right? That's just going to be e to the minus x minus v divided by v thermal squared divided by square root of pi dx. So the reason I do this is that you can see that what happens is that the line profile is just shifted by an amount, in this case, approximate to v over v thermal in x space. Yeah? So where can this matter then, except for in these unresolved? Well, it can also matter for individual sources. For example, now, if you consider a situation where, say, you have the object here, say it's a star or an active galaxy or a star, yeah? And then you have an outflow between this is you, and here you emit some continuum radiation, but then outside of this star or this galaxy, you have an outflow which moves in this direction. That is that, and it's increasing, so that if you have a point here, it has V0, have a point there, it has V1, it has a point there, it has V2. So V2 is greater than V1, is greater than V0. That is, the velocity is accelerating away from the object there, okay? Then what will happen if you absorb here between this object and you there? Well, of course, at V0 there, if this is, say, a closed line center, yeah, you will absorb something like this, right? This is your intrinsic profile. But at V1, if you just look at this, well, then you have shifted it, and if it's outflowing in this direction, then from our point of view here, we will get the blue shift. So the line profile then will just be the same, but shifted an amount, which is proportional to the line of sight velocity, right? So then you will have this, and at V2, you will have this. In an intermediate point, you will have this, etc. Okay? So schematically then, you can see that you will span out the velocities that are present in a very broad line profile, which then essentially can extend from approximately line center, nu0, minus the actual thermal width of the line, right? So if the line center is there, to some maximum frequency where you can absorb, which then will reflect the maximum velocity that you have in your outflow. Okay? And this is precise. This effect here then spans out all of these because of the Doppler shift there. And this is precisely actually how we, from observed spectra, estimate the maximum speeds that are present in stellar wind outflows. It is also how we estimate the speeds that are typically present in so-called broad absorption line quasars and other systems. So how you can actually get an approximation there for the speed. It's just a Doppler shift effect there, right? Now, that's one thing that you can do here. Now, you can also imagine another thing. I should say before I come on that if we go into more details about these type of lines, yeah, it's there don't always just have an absorption component. Sometimes they also have a superimposed emission component then, which comes from emission from all of these lines that were previously absorbed and now is gathered into our line of sight. So you, so to say, add an emission component here. And that's what then creates the famous so-called P-signal lines, as we call them. Yeah? But that's for a more detailed course in, say, stellar winds. Now, another situation that can occur, and that is over relevant, is that, okay, what if you have a sort of same situation now? You're not really forming the line in this outflow part, but you're more forming it down here, where perhaps the situation is a single orbit, but it's very turbulent, okay? So you have a lot of velocities, macroscopic velocities present, but they're moving some here and some there and some there and some there. That would be, for example, if you have seen like an image of the sun's surface of its convective rising cells up and down, right? That's a typical example of that. You know, it's not really static on average, yes. But what does this mean then? Well, that means that some of these from this parcel will have a little blue shift, another one will have a little red shift, and the third one there. So it's not going to be a systematic effect there, but what is rather going to be the case is that if this is your thermal broadening, yeah, if there were no macroscopic fields present, you would get something like this instead. Okay, now I exaggerated the effect. But you will get something that is much broader, like this. Okay, again, a bad drawing, but I think you can imagine. You just get a broadening effect, right? Okay, and that is because of the macroscopic velocity fields that can be present in a, say, a turbulent atmosphere or something like that. Or from turbulence in, say, the interstellar medium or something like that. Now, I should mention here, since we are at, so to say, at an institute specializing in stellar physics also, if you're doing it in a spectroscopy and you're not able to take these type of motions into account, that is, you don't have a suitable model that can model these macroscopic velocity fields, but rather you perhaps have a 1D static stellar atmosphere model, a classical one, which assumes that everything is static, yeah, then typically your line profiles come out too narrow and you have to artificially broaden them. And those are parameters which in different fields go by different names. In stellar physics, we typically call them microturbulence or macroturbulence, depending on the situation and what is required, okay? But that is just if you don't have these type of models for you to to be able to do it properly. All right. So that was essentially what I wanted to say about line broadening now. I did